Okay, so on today's lecture we will take a look at what we call a combined motion. Combined motion. So far we took a look at rotation, translation, and general planar motion. Now sometimes it's useful when we consider the motion of a body consisting of several motions that are taking place simultaneously. Let's take a look at the example. Let's have a swinger that can rotate this way. Let's call this body number 2. And let's have another body that is on this body, call him number 3, that can move relatively with respect to body number 2. So if we take a look on what the body number 3 is doing with respect to the frame, this is the frame, this is the unmoving plane, then we can divide this motion into two motions. The first one will be the motion of body number 2. So we will stick together 2 and 3 as it would be a single body, and we would have this motion. This is the motion of body number 2 with respect to body number 1. This is the symbolic expression. So we call this a carrying motion because it carries all the other objects. And the second motion is the relative motion. So we will disable the carrying motion, and all we will leave here will be the motion of body number 3 with respect to its neighbor, to body number 2. So this is the motion 3-2, and it's called the relative motion. So the combined or absolute motion is carrying plus relative motion. And we can express this using the symbolic equation, which then stands that 3-1 is 3-2 plus 2-1. So these symbols means motion of the body number 3 with respect to the frame equals the relative and carrying motion. Now, body number 2 is the body that is between body number 3 and the frame. Okay? Body number 3 is not connected directly to the frame, but we will want to examine that. So on these symbolic equations you can notice that body number 2 is in between, and this 3-1 equals to the resulting motion. Okay? Now, velocities and accelerations of points that are performing combined motion are as follows. So let's first do the velocities. So VB31 is VB32 plus VB21. So the velocity, we have a single point, okay, we have a single point, and we have a different motions of different bodies with respect to different bodies. So we have single point and multiple motions. This is in contrast with the general planar motion, where we had a single motion and multiple points. Okay? Now for acceleration, we have acceleration again of a single point of a relative motion plus carrying motion plus a special term that is called the Coriolis acceleration. Coriolis. The Coriolis acceleration, AB Coriolis, is 2 omega carrying. So this is relative, this is carrying. So this is 2 omega carrying times VB relative. Okay, so in this case, when we have bodies number 3 and body number 2, that would be AB Coriolis would be 2 omega carrying 2, 1 times vector multiplication VB 3, 2, VB relative. Okay? Now let's hold on for a moment with this Coriolis acceleration. So when is the Coriolis acceleration equal to 0? And actually where this acceleration component comes from. So it will be 2 omega carrying times V of point B relative. So when is it equal to 0? So when omega carrying is equal to 0, that would be the first case. So when the carrying motion is translation, that's the first case. Okay? Then when VB relative is equal to 0, well, if that's true, then we will not really have a combined motion, so this is more a theoretical case. And also when these two vectors are parallel. So when VB relative is parallel to omega carrying. Okay? So, and where does it come from? If we take a look at, for example, a merry-go-round, simple stuff. Okay, so we have something like this, and we have omega carrying here. If we take a look from above, then we will have something like this. Okay, and it's rotating this way. And we have a body here that is moving this is the relative motion. So when the body is here, then what will be the velocity of a point here? Well, it's rotating, so the velocity will be something like that. So let's call this VB. So this will be VB. Okay? If this is body number 2 and this is body number 3, then this will be VB31. Right? Now, when we have a non-zero relative motion, so it's changing its position. So let's say that it changed the position in here and it stopped there. So what will be the velocity here? Now relative motion stopped, but the absolute velocity, of course, will be bigger because it's further from the center of rotation, right? And it's a linear function. So this will be VB31. and you can see that the magnitude changed, right? So there had to be some kind of acceleration, and that would be the Coriolis acceleration. Okay, so and how will we get the orientation of Coriolis acceleration? So it all comes from the properties of the vector multiplication. So we will take VB relative, which is this vector, right? Because we were moving this way. And we rotate it 90 degrees in the sense of the omega carrying. So in our case, in this direction. So we will get the direction of AB Coriolis. And it corresponds with our little drawing here because the velocity was increased in this direction, in the direction of Coriolis acceleration. Okay. Now, a little before we will move to the example, let's take a look at the comparison with the general planar motion. So, general planar motion and combined motion. So, when we have something like, let's say, this little mechanism that is moving in a way that the final position is this. Okay, so this is, I don't know, stage A and stage B. So in general planar motion and combined motion, what is the difference? So in combined motion, we have a carrying and relative motion. So carrying motion will be 2, 1. Relative motion will be 3 to 2. So what we will have is, let's draw again the initial position, 2, 3, and the carrying motion means that we will disable this, and we will move, I will use a different color, and we will move, so this will be our carrying motion, okay, and then we will have, let's draw it again, we will disable this link, and we will perform the relative motion. So this is relative motion, and this is the carrying motion. While here, the situation is very different, because we will first, okay, let me draw again the initial position. We have a translation of a reference. So we will have translation of a reference, but no change here. Okay? So this is translation of a reference plus rotation around the reference to get to the final point. Okay, so this should clarify what's the difference in ideas behind the general planar motion and combined motion. Okay, and let me, for the final, before we will move to the example, so let's take a look at the formulas. So in general planar motion, we have velocity of point that we are examining is velocity over reference plus rotation of the point around the reference. For the accelerations AB, that is the same. That's the acceleration of a reference plus acceleration of the point around the reference. While for the combined motion, we have velocity of a point of absolute motion equals the same point carrying plus the same point relative. And AB, let's say 3, 1, is again acceleration of a carrying point plus acceleration of relative motion plus acceleration of Coriolis. Okay? So in here we don't have any indexes because all these motions are absolute motions. So if we insisted, then we could put 3, 1, 3, 1, 3, 1. All of them are the absolute motions. Okay. So let's hope that it will be more clear from the example. So let's make an example. For example, with the Whitworth mechanism. So Whitworth mechanism, so we have body number 2, body number 3, and body number 4. Okay? And what is given is omega 2, 1, and let's say on the other side alpha 2, 1. So what we have here is the angular velocity and angular acceleration of body number 2, and what we want to find out is the angular velocity and angular acceleration of body number 4. Okay, so now first we take a look at what motions do we have here. So 2, 1 and 4, 1 are rotations, right? Here is the center of rotation, so 2 with respect to the frame, it's rotation. 4 with respect to the frame, it's rotation. 3, 1, well, this is general planar motion, right? Because it's moving in this plane, but we don't know exactly how, so this is general planar motion. And now we have a bunch of relative motions. So, for example, 3, 2 is how body number 3 is moving with respect to body number 2, and that would be rotation. 3 with respect to 4, so we can imagine that 4 is not moving at all, and 3 with respect to 4 is translation. Okay, so if we want to calculate the omega 4,1 and alpha 4,1, we have to find out the velocity and acceleration of certain point of this body with respect to the frame. So we will have to write down the symbolic equations first for the body that is performing combined motion, and that would be body number 3, because body number 3 is not connected with the frame anywhere. Okay, it's only connected with other bodies, with body number 2 and body number 4. So 3, 1 is 3, 2 plus 2, 1, because there is body number 2 between 3 and the frame. And at the same time, 3, 1 is 3, 4 plus 4, 1, because there is body number 4 between number 3 and the frame. And before we will move to the equations for the velocity and acceleration, we have to take a look at the point where we will perform such analysis. And it's useful to select a point where sum of the relative motion is equal to 0. And in this case, let's call this point A. That would be point A. Why? Because in point A, and only here, the relative motion 3 with respect to 2 is 0, right? Because if there would be a relative motion of 3 and 2, then these two bodies would become separate. They would fall apart, which is not the case because there is a link here, there is a joint. So if we put all these together, 3, 2 is equal to 0. So in A, 3, 1 is equal to 2, 1, right? Because in here, body number 2 and body number 3 are performing the same motion. The trajectory and acceleration, velocity, everything is the same. So we will get the symbolic equation that 2, 1 equals 3, 4 plus 4, 1. And this is the symbolic equation that we will solve. Now, let's first solve the velocities. So we will do this in point A, and we know the indexes because we have the symbolic equation. So this is just a monkey work, right? So VA 2, 1 equals VA 3, 4 plus VA 4, 1. Now, point A is given because this is where this symbolic equation takes place, and the indexes are taken from the symbolic equation. Now, all we have to do is to actually solve the equation. So we will go one term at a time and see if we know direction or if we know the magnitude. So for 2, 1, that's how body number 2 is moving with respect to the frame in point A. Therefore, we know everything, right? Because we know omega 2, 1 and we know the distance. So velocity of point A of 2 with respect to the frame is somewhere here. So this is VA 2, 1. And the magnitude is omega 2, 1 times the distance between A and this point. So we have to call this point something. Let's call it O21. So that would be A O21 distance, sorry. Okay. So now when we continue, we will take a look at the relative motion. So this is relative, this is carrying. And the relative motion is 3 with respect to 4. So how body number 3 is moving with respect to 4. So we know the direction, right? Because the direction of the motion is given by this joint, and that's translation. So this is direction of VA3, 4. And we know direction. We don't know the magnitude. And 4, 1, now this one might be a tricky one because this is the motion of body number 4 with respect to the frame in point A. Now point A is not directly on this body, it's here. But still, motion for 1 is rotation. So it doesn't really matter where the point is because the direction is always on the tangent, right? So you can imagine that this body number 4 is like everywhere and it's rotating. Therefore, in here, we will have direction of VA4, 1. And we can solve this equation because we have two unknowns and it's a vector equation. Okay, so to do so, we will have, this will be VA 2, 1, and that equals direction and the other direction is here. Okay, so this one is VA21 and it equals those two, so 1, 2, so we know directions. So this is VA41 And that is what is of our interest, right? This is VA34. So from VA41, now we know how big it is, right? And from here we can calculate omega 41, which is something we want to find out. And that would be VA41 divided by the distance from point A to the center of rotation, which we will call, for example, A041. So it will be A041. And we have the first part of our example, yoo-hoo. So now we can move to the acceleration, and the equation goes from the general equation, so it will be AA21 equals AA relative 3,4 plus AA carrying 4,1 plus AA Coriolis. Now, all we have to do is to solve this equation, and 2,1 is rotation, therefore it has two components, normal and tangent. For those components we know everything, right? Because we know omega, we know velocity. This will give us the normal component, and we also know tangent component because we know alpha to 1. So in here the normal component is VA21 square divided by the distance, so that's A021. And for tangent component it's alpha to 1 times the distance A021. A021. Okay? So where will it be on the figure? Well, in here we will have the normal component, and in here we will have a tangent component. So this will be AA21 normal, and this will be AA21 tangent. Why is it going this direction? Because alpha is going that direction. Okay? Components 3,4. 3,4 is what motion? 3,4 is translation, so it only has one component, and we know the direction is the same as direction of velocity. 4,1, well, 4,1 is rotation, and rotation in here, so it has two components, normal and tangent, and for the normal we know everything, right, because we know velocity. So in here there will be a normal component AA41 normal. Its magnitude will be VA41 squared divided by the distance A041. And we don't know for the tangent, the direction is the same as direction of velocity. And the final one is Coriolis, and Coriolis in this case is 2 omega carrying 4,1 times VA relative 3,4. Okay? So omega 4,1 we know from here, right? And VA34 we know from here. So for the Coriolis we know everything. We know both direction and the magnitude, because this is the planar task, so the magnitude is 2 omega 4,1 VA34, and the direction, well, we will take VA34, which is here, so we will take VA34, and we will rotate it 90 degrees in the direction of omega carrying. Omega carrying, where does it go? So VA41 goes this direction, it goes down. So 4-1 is rotating left. Okay, so this will be omega 4-1. So we will have to turn VA34, VA relative, 90 degrees. So this will be the direction of AA Coriolis. And now we have everything we needed, right? Because we have one unknown, second unknown, so we can solve it. So just to be sure that you can do it, we will go one term at a time. So VA21 normal, that's this one, so it's this one, plus VA21 tangent, this one. Okay, so this is the left side of equation, and that equals, and now we will go through everything we know in particular, which is AA41 normal. So it's here, AA41 normal, plus Coriolis, plus these two directions. So 1 and second one. So these two are perpendicular. So this is the left side of equation, jump, jump, and that equals 1, 2, 3, 4. So this is where we will get all these little arrows. So this is AA34. And this is AA41 tangent. Okay, and this one is important because from here we can calculate alpha 41 as AA41 tangent divided by the distance, which is A041. Okay, so hope this is clear, and you can use the combined motion approach because it's a general method that you can use for any type of the mechanism.